Okie dokie. Can everyone hear me? Sweet. And feel free to use your mic if you would like to, or if you just want to use the chat, feel free to do that as well. So basically, I've got a bunch of problems that people have requested that I do. So I was going to start doing those first, and then we can go back and maybe do some other practice problems, if that sounds all right with you. So I want to make sure we get to all of the ones that people asked for. So kind of in order, starting from section 2.1. Section 2.1 is kind of dealing with like the concept of like rate of change and like derivatives. And so from 2.1, I think asked us to do problem 22. So this is page, will respond to me, page 96. And so the question goes, on October 17th, 2006, in an article called U.S. Population Reaches 300 Million, the BBC reported that the United States gains one person every 11 seconds. If F of t is the United States population in millions t years after October 17th, 2006, I'm just going to write that down. I'm going to say that F of t, actually, I'm going to call it P of t. Doesn't really matter what I call it as long as I know what I'm referring to, and I like the idea of having population dependent on time just much better. I think it makes more sense. So P of t is a function, and it is the U.S. Population t years after 2006. So when t is equal to 1, we'll be talking about 2007. T is equal to 2, we'll be talking about 2008, et cetera, et cetera. Now it wants us to determine the meaning of P of 0 and P, or determine the values of P of 0 and P prime of 0. Do you know what P of 0 would be? Do you have your book in front of you also? Because if I just kind of read it out loud, then probably wouldn't remember. You're saying that P of 0 is equal to 0? Why are you saying that?
$300 million.
Yes, 300 million. So P of 0 is equal to 300 million, and we're saying that it's measured in millions. Actually, let's just leave it. I'll write down 300 million. That's better. So 300 million. And so this is just at time is equal to 0, which is in 2006, what the population is. And then what would P prime of 0 be? So one thing that I find helpful that we did in this like chunk of like sections is to write things in Leibnitz notation, which is something that looks like this. So generally speaking, this is P prime of T. So what does this mean? This means we're looking at the change in population with respect to time. That's how you kind of read something with Leibniz notation. You've got your change in blank with respect to blank, top to bottom. So the change in population with respect to time. So we know that we're looking at the change in the population, again, with respect to time, at t is equal to 0, or in 2006. So one thing that we can also look at is the units that maybe we would use. So it would be people per unit time. And so do you have an idea of what that might be?
Wouldn't it be undefined?
Why do you think it would be undefined?
Because you can't divide anything by 0.
We're not looking at, this time is not quite t is equal to 0. This unit time is like per year, basically, or per min. And what that's saying is that this isn't necessarily at like t is equal to 0. What we're doing is we're getting t really, really close to 0 so that we can determine what the rate of change is. And so this rate of change, we're not going to be using t itself. It'll be like dt. So time is like changing. So it's not going to be undefined. That's a good thought. Always keep an eye out for places where things could be possibly undefined. But what they're actually looking for here is 1 over 11, not 111, 1 over 11 people per second. So what this is saying is that every second, or rather every 11 seconds, an American is born, or the population of America, maybe not born, maybe immigrants. The idea is that an American, like the American population rises by 1 person every 11 seconds. And the t is equal to 0 refers to this occurring at 2006. So this number is not accurate in 2007. This number is only applicable at the specific point in time where t is equal to 0, or we're existing on October 17th, 2006. On October 18th, 2006, this number may be slightly different. On October 19th, certainly years in the future, this number will very likely be very different. But at this time, t is equal to 0 in 2006, it is 1/11 of a person per second. Does that kind of make sense? And I know, you don't get 1/11 of a person per second. That's why it's kind of framed in that 1 person every 11 seconds. But math-wise, that's the number that we would use.
So this question wasn't looking for calculations. It was more looking for definition.
Yeah. So we were mostly just looking to like pick out of this problem which numbers were which. There wasn't really an equation that we could do much calculations with. We just wanted to get a little bit more familiar with what a derivative is, how change like looks in terms of like the math that we're going to be doing. So yeah. Any other questions about this? All right. So I've got another couple of problems requested from 2.2. And for everyone who's just joined us, I've got a couple of requests for problems, and I'm just going to go ahead and do those first, just so that we can make sure that all of them get done. And then we're going to circle on back and maybe do some more practice problems if we got the time. So I'm in section 2.2, and I'm going to be doing a series of, I'm going to be doing 1, I'm going to be doing 5, and I'm going to be doing 9. And these are, the first 2 are going to be taking graphs and graphing the derivative of the function. So the way that I do this is, and I am going to show you both the original regardless. Sometimes I don't draw the graphs because they're in the book, but this is really important that we see exactly what's going on here. And my line is going to look something like this. See a little bit so you can see what these numbers are. So this is 1, and this is 2. So this is my original. And I need to graph it. One thing that I do just to start off with, and this is jumping ahead a little bit. This is like when we're looking at like algebraic like functions, how do we find a derivative? But it's something that I like to think of when I'm doing these graphs, is that if I have a function, y is equal to x, which is not exactly what this function is, but it's of this form, we have a linear function, basically. So can everybody agree with me that this function is linear?
Yes.
All right. So if I were to take the derivative of this, algebraically, it would give me a constant. And I'm going to show you graphically what that looks like. In that I go from a y or an x to the 1 to taking a derivative, and I'm going to get x to the 0, or not x to the 0, but I'm going to get just like a constant number. And one of the reasons for that is that we think of derivative as slope, right? The slope of the tangent line. So what is the slope of the tangent line to a line? Any ideas?
-2.
Yes. In this case, it will be -2, because the slope of the tangent line to the line is going to be the line itself. There's no way that I could draw a tangent line on anywhere on this line where it just wouldn't be the line. So we have a constant number. The slope is always going to be -2. So the derivative graph is constant, and it's a constant -2, which is the slope. What would the derivative of this graph be, this in the green? If I were to draw another graph, what would it look like? Any ideas? what's the slope of this line?
Zero.
Yep. So if I were to graph the derivative of this, it would just be flat along 0. Because my slope is 0. So algebraically, you'll see in like later sections that this is kind of like what's happening. And like logically, when we talk about derivatives as being slopes, then we just need to analyze what the slope is where, and it will give us our answers. Are there any questions about problem 1? Okay, let's give problem 5 a try. Give me just a second to get this drawn. So with problem 5, I know why they have you starting to draw derivatives this early, but a lot of the techniques that you will learn later on would make this a lot easier to do. So it's like not the easiest of processes. Okay, so it looks a little something like this. So what I do, or at least, how about we do this? Does anyone have any ideas of where maybe we should start?
Would you start by looking at where I guess the slope is 0 for this particular graph?
That is exactly what I would do. The slope is going to be 0 at these peaks and valleys, essentially. This is where my tangent line is going to be flat. So, because remember, we're not just looking at like the slope of this thing, we're looking at the tangent lines. So this is where the tangent line is going to be flat. So that's going to be, I'm just going to go straight down. I'm not really going to look at the numbers very much because the numbers are a little off for this one. So just something that looks like this. So these points are going to be 0. All right. What do you think may be next?
Where it's increasing and decreasing?
Exactly. So let's break this down into, it's going to be decreasing from here to here, which is going to be analogous from here to here. And it's going to be decreasing from here to here. So I'm just kind of bracketing off parts of this graph. At least that's what I do to kind of help me visualize it. And then increasing in the area between these two. And notice that in order to transition from decreasing to increasing or from increasing to decreasing, we have to transition through 0. So that kind of gives like a good like marker system. Okay, so what does it mean to be increasing? What is that derivative going to look like on a derivative graph? If something is increasing, the derivative is going to be?
It'll be positive.
Exactly. And then if it's decreasing, it'll be negative. So we know, and this is just something that I do before I get to like bogged down in some specifics. I know I'm going to be doing something negative, I'm going to be doing something negative, and then I'm going to be doing something positive. So now I can kind of see a shape beginning to form. But I'm going to go ahead and I'm going to prove it, that we are going to have something that's kind of almost like a parabolic shape. It's like this upside down curve. Can you guys see my mouse moving? Can you like see the pen even if I'm not drawing anything?
Yeah.
Yes.
Okay, awesome. Okay, so I'm going to start with my decreasings. I'm going to say that I need to compare at 2 points. I'm going to pick this point and this point, what the slope of the line is that is tangent to the curve. So here I'm going to say the slope is probably pretty analogous to the curve. It's going to look maybe, get an actual straight line tool. It's going to maybe look something like this. And then here, I'm going to say it's a little something like this, because it's like it's curving down towards 0. And I can see that if I were to draw another point, it might look something like this. Okay, right here. So you can see that my slope starts very negative, and then as my x increases, so as I move from this point to this point, which is a higher value of x, it's less negative, and then less negative, and then eventually 0. Are we okay with that?
Yeah.
Then the way that I'm going to draw that is I'm going to start by being most negative further out, and then as x increases, it's going to be less and less negative until it reaches 0. And then I'm going to do something pretty similar over here. I'm going to say that I have a point here, I'm going to have a point here, and then I'm going to have a point here. And I'm going to kind of be able to see these same types of lines. Maybe this line looks like this. And then this line looks like this. And then this line looks like this. So it's getting more and more negative. So we're just going to do the exact same thing. It starts off less negative and it gets more and more negative. So it looks something like this. Now for the top part, the positive part. Whenever there's a curve like this, we talked about concave up and concave down already, right? Sorry, I do 2 calculus classes, and we're both doing Calc 1, so I just want to be sure that we talked about the things that I think that we talked about. We spoke about concave up and concave down. Yeah, you're not.
Yeah.
Sweet. Okay. So there's a point where we transition from being concave up into being concave down. And that point is called the inflection point. And so everything to the left of this point is concave up, and everything to the right of this point is concave down. And that point is going to be where, and it's usually about like halfway between these curves. You can maybe not halfway, but you can pretty well like visualize the inflection point as like the transition point. So that point is going to be where the slope is at its maximum. The slope is going to be its highest right there. And then before the inflection point, it's going to be increasing. So we start off with something that's a little bit bigger than 0. Maybe it's not going to be at 0. It's going to be like this, like a point there, and then a little bit higher. It looks like this. So we start close to 0, and then we're increasing, 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 and then we hit our maximum value, which occurs at this inflection point location. Same like drop down X value. That's kind of why I did them one on top of another. So let's just drop it down. That's the X value where the inflection point happens. And then after that, we're going to have points where it goes from its inflection point, and it's still positive, but it's coming back down, and it's approaching 0. So it's kind of flattening out in terms of like what the tangent line looks like, and in our derivative graph, it's going to come back down to, it's going to approach 0. So that's kind of what this derivative graph is going to look like. We broke it down into decreasing and increasing. And then this part where we had to transition from concave up to concave down, we can see where our maximum slope is, which is right at that transition point. So, yeah. Any questions about this?
So in the book, it shows that it's curving back up on the right.
Let me see specifically. Yeah, okay. So if we were to continue this graph, number 5 in the book has something that kind of looks like this, almost like a little hook. And we could envision the graph continuing to hook back up, which would give us kind of like a sine type wave, or like a cosine type wave. And the idea is that here there would be an additional 0. So if we were to draw that in, there would be a 0 here. And then there would be an inflection point somewhere on this line. Now that you say it, I can see that curve, and I can see it approaching that 0. So this orange chunk is going to be scrapped. We're going to find out where that inflection point is, which is going to be about right here-ish. And so that is going to be our lowest slope. So there's our most negative slope. So this orange part here is going to come down to the most negative part. And then, it's just color-coded. And then it's going to have a line, and then it's going to be approaching the slope equaling 0 again. So we would loop back up to where it equals 0. And then we would say that this point onward is going to be increasing, and it will be positive. So we would have, just another chunk of this where we were getting larger and larger and larger slopes. And if we were to continue this graph onward, if I were to have something that just, a sine wave that did this over and over and over again, its derivative, let's call this y is equal to sine x. The derivative of this is going to be equal to cos x. So it's going to be the same type of graph. It's just going to be offset a little bit. Something that maybe looks like this. So not quite, but not the most precise of graphs. But when we get on to the algebra part of this later, we're going to be able to see that if we take the derivative of sine, we get cosine. And you can see here where we have our minimum, we have a 0, where we have our maximum, we have a 0, and in between we have a peak. And that's kind of just that shift from sine into cosine. Does that kind of make sense? So they're both repeating curves, basically.
How do we know what the y value should be, though?
We could guesstimate that. I don't usually worry about that too much in these types of problems, but if you want to go through and do that, we definitely can. I would say that this, I would probably do it, gosh, see, these numbers are so wonky. That's why I didn't really bother. This point here, I think that looks to me to be like a negative 2.25. This would be negative 2.25, comma, what do you think, negative 2.5?
Yeah.
And then I would pick a point like maybe, let's see, this is going to be, inflection point at maybe negative 0.75, comma, we're just going to call it 1 for the sake of our sanity. And then the idea is that the more accurate, to be more accurate, you would take the smaller and smaller increments. So I would take like a chunk from like here to here, and I would use that to find the slope around the inflection point. So maybe I would do the slope from negative 1, it's not really negative 1, 0 to what is that, 0, 2.5. So our delta y is going to be 2.5, and our delta x is going to be 1. Is that what I wrote? Yeah. So our slope from here to here is maybe about 2.5. We could get more specific by just taking more slopes and like doing more like precise approximations, but because of the way that this graph is situated, I would say that that's about as close as you're going to get, about 2.5 there. Does that kind of make sense?
No, I'm still confused about, I think I never know where to put the top and the bottom.
If they really are trying to eke out a number from you for the top and the bottom, what I would do, I'm going to erase some of this just because it's not helping this part. Problem solving. Just 1 sec, sorry. So the idea is we're going to try to pick, we're going to try to find the slope at a given point. The slope of the tangent line at a given point. And I'm going to call them the light blue point and this neon greenish point. Because these are the points where we said we were going to have our maximum and our minimum, correct?
Okay, yeah.
Stop me if you have any questions about what I'm doing. We know that these blue points are 0. We know that these are zeros. The nature of this graph is that we're not really going to know much about the slopes in between these, I think, and I think that that's fine. Like the slope of this dark green line here is not like something that's concerning us. But if we wanted to find the max or the min, what we would need to do is find the slope at this blue point or this green point. So to find the slope at the blue point, which we said was approximately negative 0.751, would you say that's about the inflection point?
Yeah.
Okay. And now we have at this green point, which is maybe, let's call this 2.751. So these are like not nice numbers to work with. I would not choose to work with these numbers. So the idea is that we can find the slope between these two by like doing, like, do you remember when we did like triangles? We would do rise, like how far we went up, over run, which is how far we went over, and that would be our slope.
Yeah.
So our rise, which I'm going to call delta y, from this point below and this point above, I'm looking for just like easy points that I can like work with, which is a little bit harder because this graph doesn't cross a lot of good points. I would say maybe this point here at we'll call it 0, so it would be up a little bit. 0, wait, did I name this point well? This should probably be, sorry. This might be closer to negative 0.51. And then this, we're going to call negative 1, 0. And then this point we can pick to be we'll call this negative 0.25, 0.252, maybe. So we're going from a y is equal to 0. A delta y is going to be from, it's going to be y2 minus y1. So we're going from y is equal to 0 to y is equal to 2. 2 minus 0, 2. And then our delta x, our change in x, is going to be going from negative 1 to negative 2.5. This is going to be no, we're positive, 0.75. This is 2 over 3/4. So I'm just going to divide by a fraction, which is going to be 2 times 4 over 3, or 8 over 3. So I would say that this is 8 over 3, which is a little less than 3. Because that's my slope. Delta y over delta x is my slope. And my slope is going to be here, 2 over 3/4, which I'm simplify down to 8. Are you okay with that?
Yeah.
Okay.
Thank you.
And then we could do the same thing for this green point, where we pick 2 points along the side, and then we find the slope, which is going to be negative in this case, and that slope would give us perhaps an approximation of the tangent line to the curve, which we could use to graph it like this. But yeah, that's what's up there. Any other questions about number 5?
Nope.
All right, let's do number 9. All right. So number 9, we have a graph that's not quite a sine wave. It's like a curve, though, a lot of that type of kind of look. it looks a little something like this. Something like that. Actually, I'm going to redraw this so that some things are a little bit more clear. Okay. Keep trying to like make it even, and it's not even. There we go. Okay. So then we have several points. We have this point, which is x1. We have x2, x3, x4, x5, and x6. And this question is asking us to find several things, including where f of x is the greatest, where f of x is the least, and then where f prime of x is the greatest, and where f prime of x is the least. And I should have marked these points. Okay. So what are your thoughts on where f of x is the greatest? And where f of x is the least? It might be handy to look at the actual graph of this in the book because it's probably a little bit more specific than what I've drawn here.
Would x3 be the greatest?
Yes. So literally what this question is asking is what y value is greatest? And for this is going to be x3, because it has the greatest y value. And this type of question, we can look at f of x being like equal to y, because this is just like the graph of the function, the original function. So what about the least? And I got to redraw one of these points. It's deceptive. It would be the least at which of these points?
x4.
Yep. So now we get to ask the question, where is f prime of x greatest? And where is x prime of x, f prime of x least? Any ideas?
Greatest would be x5, right?
What do you think x5?
Has the largest slope at a singular point.
Yeah, I'll buy that. Yeah, I think I wrote down x1, but looking at the original graph, x5 is probably steeper, because it's a little bit closer to the inflection point of this. So it would maybe look something a little bit more like this. Yeah, x5. And then what about least?
6.
Yep. This is 6, not 4. So x6 is going to be the least because it's just coming off of this 0, and it's still in this really flat part of the graph. So x6 is going to be the least.
So are we basing this off of your graph or the graph in the book? Because
We're basing this off of the graph in the book. I just tried to sketch it out so that maybe it could be seen a little bit better.
I don't think x6 is the answer for the least in the book.
I'm looking at the book and I see a couple of potential options. One might be x3, one might be x4, and one might be x6. X3, I think, looks a little something like this. If I have this curve kind of blown up, I think x3 is about right here. So I would kind of draw something that maybe looks a little like this. And then for x4, we have this curve here down at the bottom. And x4 is right here. And it would have something that maybe looked a little like this. And again, I'm kind of exaggerating this a little bit and blowing it up. And then x6 looks something a little like this, and x6 is right here. It's just off the 0.
So just based off of that, and I'm just need to clarify this, I guess. Could we eliminate x4 from the answer because it's got an increasing slope, or is that like the wrong way to think?
All right. What if they are not looking for the one that's closest to 0, but looking for the most negative? That's what we answered for number 1. You're right. I'm sorry. I was looking for something that was the closest to 0, and that was the wrong frame of thought. So this is x6's closest to 0. X4 is positive. X3 is negative, and it is, besides x6, the only negative slope, and it is more negative than x6. So you are right, this is also x3. Sorry about that. Sometimes these questions ask you to frame it as like which is closest to 0, like which is the absolute value is the smallest, but that is not what this question is asking. This question is asking for the most negative, and the most negative will be at x3 of the points that they've given us. So sorry for the confusion there. I hope that clarified things a little bit better. As like a follow-up question, do you know where the most negative slope in this whole graph would be? So we said that slopes were at their minimums and maximums. Slopes are the largest at inflection points, where we're making that swap from concave down to concave up. So our most negative slope in this whole graph, like not given just by these points, but the entire thing, is going to be at 0, 0. This is most negative. Yeah. Any questions about that? Sorry again about the confusion. Okay. Let's maybe give a couple of questions from 2.3 a try. Okay. So 2.3 has us doing some interpretations. We're going to start with question 5. And let me check what page I'm on. I'm on page 108. And so I have a problem that says the time for a chemical reaction, T in minutes, is a function of the amount of catalyst present A in milliliters. And then it says T is equal to F of A. And I think that's ridiculous. Why do we not just have the function T of A? So the first thing I would do is to say T of A, because that's what we're looking at. So whenever I see an F function, I'm just going to replace it with my T function. Everybody's cool with that. Part A says that if I have T of 5 is equal to 18, then it wants me to give the units of 5, the units of 18, and to talk about what the statement tells us about a reaction. And then for part B, it'll give us T prime of 5 is equal to negative 3. And so it again wants us to give the units and then talk about what it means. So any idea what the units of 5 is for part A?
Minutes.
I thought it would be milliliters.
The answer is going to be milliliters. And the reason, do you want to explain why that is?
Well, I took 5 to represent the A in the equation. So I was just going off of what the, I guess the book said. It said A in milliliters.
So if we said very generically, we have this function, it could be, you know, A cubed. It's not going to be A cubed, but it's some function of A. And the way that we would solve, for instance, a function, if we were given A, like, you know, times 2 plus 4 or whatever, is we would put in 5 here. We would substitute 5 in. So we know that this 5 represents the milliliters. So this chemical reaction depends on how much of the catalyst is there, and the catalyst is added in milliliters. So yeah, 5 milliliters. What about 18? What do we think the units of 18 are going to be?
Well, that would be the minutes.
Yep. So here we have basically T is equal to 18. So we have, that might be why they kind of split it up so you can more easily visualize that T is equal to F of 5 is equal to 18, which just explicitly says 18 minutes for this reaction to happen when we have 5 milliliters of the catalyst, which kind of answers the rest of this question. And that all right. So that's kind of part A. That's just kind of looking at a function and analyzing it. Let's think a little bit about its derivative. So now we have T prime of 5 is equal to negative 3. What are the units of the 5? It's a little bit of a trick question. Still in milliliters. The 5 doesn't change. This function, we're taking its derivative, but we're still having it be dependent on the amount of catalyst that we add. So the 5 is still going to be 5 milliliters. If you think of those graphs that we did in the previous section, how we would drop down from one to another and say, like, the x value of this is going to be the same in these 2 points. For instance, when we had like a peak value where a function was at its greatest and the derivative was equal to 0, the x value was the same where the function is the greatest and its derivative is equal to 0. So essentially that same kind of thing is happening here where we have a derivative graph, but it's still, we've got that x-axis, in this case measured in milliliters, that it's dependent on, or a-axis measured in milliliters. All right, now for a little bit more of a tough one. What is the units of the -3?
I'm just going to completely guess and say minutes per milliliter. I don't know.
That's good. So it's -3 minutes per milliliter, but yeah, I didn't write that down. And so one way that we can kind of visualize that is if we use the Leibnitz notation. So problems, this is problem 5, but problems 1 through 4 had us doing Leibnitz notation for a variety of problems. And as I kind of mentioned, I think Leibniz notation is really good in some aspects because it kind of lets you visualize you're taking the derivative of time, or yeah, you're taking the derivative of the time with respect to the amount of catalyst added. So this is, you can kind of envision how these units look like. So this is how many minutes the reaction takes based on how many milliliters of catalyst added. So exactly, that's one great way to visualize it, I think. So yeah, so we have -3 minutes per milliliter. Now what does that mean?
Is it saying when you have 5 milliliters that you're going to decrease the reaction 3 minutes for every new milliliter you add?
Exactly. That's exactly it.
Okay. I was a little confused on that as I was saying it, but
yeah, it's like sometimes saying these things is like really weird because it's like not language that we would usually use, and you're kind of like bending over backwards to like make sure that you're being like perfectly accurate. But yeah, adding 1 more milliliter would decrease the time by 3 min, or T would be affected by, trying to like think of a good way to put this, but we would just say that there's -3 minutes per milliliter added. And usually the way that we describe this is by adding 1 more milliliter, just because like once we get to 6 milliliters, this number might change. T prime of 6 might not be -3. It very well might be, but it also might not, and we don't really know. So we want to keep it as close to 5 milliliters as possible. But yeah, inversely, if we were to only add 4 milliliters, we can estimate that our time would then be 18 plus 3 minutes. So it'd be 21 minutes instead of 18 minutes. So what does that kind of tell you about the catalyst at 5 milliliters? Is it speeding up the reaction? The reaction is going to take less time with more catalyst. That's kind of what I was going for. So adding more catalyst means that it takes less time, which makes sense in terms of chemistry. So yeah, any questions about number 5? Okie doke. Let's try one more from section 2.3. I believe it was, let me get my book to scroll, maybe, get to it. Number 9. So this one has a lot of biology lingo, and my major is microbiology, and so I know these terms like tangentially, but like even reading this, I was just like low-key overwhelmed. with all of like the lingo that they were using. So a lot of like the challenges sometimes in these word problems is just parsing through all of this example language to get to the math of what they want you to do. So for number 9, question goes, when you breathe, a muscle called the diaphragm reduces the pressure around your lungs and they expand to fill with air. The table shows the volume of a lung as a function of the reduction in pressure from the diaphragm. So I'm going to say that this is a function V of P. So the pressure around the diaphragm is going to impact the volume of air in the lung, or just the volume of air in the lung, which is measured in liters. Then pneumologists, which are lung doctors, define the compliance of the lung as the derivative of this function. So compliance is dV dP. So what are the units of compliance for question A? Estimate the maximum compliance of the lung for question B, and then explain why the compliance gets small when the lung is nearly full, which is around 1 liter. So what are your thoughts on the units of compliance?
Liters per centimeter of water.
Yeah. So based on this table, we're going to be doing liters per centimeter of water, which is a way of measuring pressure. All right. Now, estimate the maximum compliance of the lung. So what we want here is the maximum dV dP. How do you think that we could maybe do that?
One over 30.
1 over 30. Oh, so keep in mind that we're not just dividing volume by pressure. This is going to be like some sort of a curve, and we're looking at the tangent line to that curve. And once it's getting close to its maximum, the tangent line is going to be like approaching 0. So 1 over 30 is not going to be our strat. Let's think about what a derivative is in its graphic sense, like talking about a graph. What is the derivative?
It's the slope.
Yep. So what is one method we have of getting slope? We did this a little bit earlier. We can estimate slope by taking delta y over delta x. So the way that we can do this, or the way that I did this at least, would be to do this for all of these. Sorry, I'm like looking at the table here and trying to gesture to it, not realizing that you can't see my book. So we have this table going from like 0 to 5. So I would say our delta y there would be 0.29 minus 0.20 over 5 minus 0. So this is 0.09 over 5. And we would have to just start putting stuff into calculators in order to get this. So this is going to be, calculator will work, 0.018. And then we do this again for the next two sets. We have 0.49 minus 0.29 over 10 minus 5. So this is now 0.2 over 5. And you can kind of see that this one is going to be larger. So this is going to be 0.04. And now we have 0.7 minus 0.49 divided by 5, because again, we're going from 15 to 10, or 10 to 15 rather. And this next set is going to be, sorry, I'm just putting these in my calculator now, and feel free to put them in your calculator as well to kind of follow along. But it's the same math that we're doing. We're just taking one part of the table and going, like jumping up incrementally. Then 0.86. And this is 0.32 or 0.32. And I'm going to stop here because I know that as we continue, it will continue to get smaller. Right? Does that make sense? So for this next one, it's going to be 0.1018. So our peak, our maximum, is going to be approximately 0.042. And we're saying that that occurs when P is approximately equal to between 10 and 15. So we'll say that's approximately equal to, like, I don't know, 13, 12.5. Somewhere in between there, the slope is at its largest. And then it will continue to decrease. So what does this kind of look like? If we were to kind of sketch out a graph, it might look something a little like this. We start off with a smaller slope, and then our slope gets larger and larger, and then it starts to come down again. And our maximum slope is going to be here. This is 0.042. And then we have these other points, for instance, 0.018, where we have that here and here. So yeah, you can kind of see the shape of this graph that way. Does anyone have any questions about how I found that maximum compliance? All right. I'm taking silence to mean that there are no questions. Awesome. Stop me if we're not on the same page. And we can talk about problem C, which is explain why the compliance gets small when the lung is nearly full. So it's asking us very specifically about why this curve comes down. Does anyone have any thoughts on this? Okay. Stop me if you have a thought that you'd like to kind of share. But basically, what I think that they're going for here is that the units of compliance are liter per unit pressure. So the idea is as pressure increases, as pressure unit per unit pressure reduction. It's a pressure reduction that's making this occur. So as the pressure decreases from its, I don't know, base position, then the volume will be able to increase. And so you'll get like a larger, it's a greater impact on an empty lung is kind of what they're going for. If your lung has no or virtually no volume in it, they're starting off at 0.2, and that's because your lung doesn't actually expel all of its air when when you breathe out. So your volume is at 0.2 at its like lowest point, and then by reducing the pressure a little bit, you get more volume, and then you approach a point where at about 12.5 pressure centimeters of water that you've reduced, basically that around that spot, around this spot, like in this X range or pressure range, that's where you're getting the most bang for your buck, the most volume per unit of pressure that you're reducing. So that's why the volume is increasing. So when we say our max dVdP, what we're saying is that we're maximizing the amount of volume we get from our lungs in air, the amount of volume of air we take in per unit pressure we're reducing. And it makes sense going up to that point that as we are reducing more and more, we're getting more and more volume out. But at some point, our lungs start to get full. And even like reducing the pressure by a lot, there's just not much more air that we can physically take in. So we hit our limit at about 1 liter of air, and then we start to exhale. Does that kind of make sense? This is like, the reason this problem is really tough is because the units are so wonky. Because we usually, we have like time on the x-axis, and that's like something that's a lot more digestible than we're alternating the units of pressure that we're reducing this by, and that's affecting our liters. But the important kind of things to pick out from this problem are that we have a function. Volume is dependent on pressure. Pressure is our independent variable. So what we're going to kind of play with on our x-axis is pressure, or pressure reduction. Roll my eyes, sorry. Pressure reduction is what we're dealing with. And then our compliance is going to be our liters per unit pressure reduction. And then our maximum is going to be at some point where we can maximize our liters per unit of pressure that we've reduced. And that point, after that point, it starts to get harder to add air into the lungs. And you notice that this is a pretty steep drop off. So, yeah, this is the graph of the derivative, by the way. The graph of the original function would look something along these lines. We would start at 0.2 and we would end up at 1. So we'd start, it's kind of like a little curve. We would have an inflection point here. And it would be this point at the same x value. Okay. Are there any questions about that? It's a little bit of a long-winded explanation. I hope me talking didn't just make it worse. Is everybody kind of on the same page with what's going on here?
Yeah.
Awesome. Okay. We're sitting around an hour and 15 minutes here. If people want to continue, I can certainly do some more problems. But this is usually about where I wrap up. So, questions, anyone? Anything you'd like to review? Anything you'd like to talk about?
Is there anything else you feel like we should be focusing on for this section, other than what we've already covered?
Honestly, I think you guys did a pretty good job of picking out which problems were relevant. I think 1 through 4 in 2.3, the Leibnitz notation ones, we kind of did that in 5. Just being able to read Leibnitz notation and be like comfortable saying this is the derivative of volume with respect to units pressure reduction. And that's just kind of how I would read a piece of Leibniz notation. I think that's important for being able to continue. It's not as important as I'm making it out to think for 110, but I think it's important for understanding what's actually happening in describing derivatives. But other than that, you guys are sitting pretty well. I think it's not next week that we get into like calculations. Next week we're talking about like second derivatives, marginal cost and revenue. So a lot of this is still just like conceptually, like how do we explain rates of change? And so if you're feeling pretty comfortable with the concept of a rate of change, then you're sitting in a great great spot. I don't know if that really answers your question, but yeah. The graphing ones are the ones that always get everybody. So the graphing ones are the ones that always get me. So it's just a lot of practice. Unfortunately, there are a bunch of graphs in Route 2.2 to practice on. Any other questions? Well, thank you all for coming. I hope you guys have a wonderful evening and a wonderful week. And I will see you all next week.
Thank you.
Thanks.
Have a good night.